Thank you for joining the Atto Fridays today. Our speaker is Professor Giuseppe Sansone, and he is now in Freiburg. He was a visiting scientist at the Max Planck Institute for Nuclear Physics from 2009 to 2011. Then he was an associate professor in the physics department at the Polytechnic of Milan from 2014 to 16. And since 2016, he has been full professor for experimental physics at the University of Freiburg. And in 2020, he was awarded the Innovation Award on Synchrotron Radiation 2020 Helmholtz Centrum Berlin. And his research interests include attosecond dynamics in atoms and molecules, generation of ultra-short pulses, and free electron laser science. So today, we're very happy to have him here. He will talk about attosecond metrology at free electron lasers. So the floor is yours. Feel free to start.
Okay, thank you very much for the nice introduction, for the invitation, first of all, and also for this nice presentation. I hope now you can see my screen.
All fine.
I will also try to have the laser pointer. Perfect, so everything should be fine. So, as Carla was mentioning, I will discuss about attosecond metrology at free electron laser and also some latest development of how using these, the technique that I will show you as an attosecond timing tool for free electron laser experiments. That's why I slightly changed the title. Just to be sure that I will not run out of time, let me thank all the person involved in this work from the very beginning. I will discuss about free electron laser experiments, and this is usually done in large collaboration. Here you can see the different institutions involved, but in particular, I would like to thank the people that you see highlighted in red. From my group, Praveen was the major actor in the data analysis. And then we have a strong support, of course, from the people at the free electron laser, in this case by Fermy, the free electron laser in Italy. The machine group represented by Enrico Allari and Luca Giannessi. And then the group at the end station, Carlo Callegari, Kevin Prince, Cesare Grazioli, and Michele Di Fraia. So free electron laser are, would say, proliferating worldwide. The very first one who come into operation in the soft X-ray or extreme ultraviolet was Flash, now more than 10 years ago. In Hamburg, here in Germany, there is a second free electron laser operating in the X-ray, which is the European XFEL. But in the meanwhile, there have been several projects worldwide in the US with LCLS, in Japan with SAGLA, PAL in Korea, and so on, where generation of X-ray light has been demonstrated using these large-scale facilities. Today, we'll address in particular the seeded free electron laser Fermy, which is operating in Italy. So Fermy has a kind of unique characteristics, which makes, very interesting for the experiments that you are performing. So it's a seeded free electron laser. So this is the main difference with respect to the other free electron laser operating in this energy range. It means that it employs a seed wavelength in order to create the soft X-ray or extreme ultraviolet radiation. The seed wavelength, it's in the UV around 260 nanometers. And thanks to the seeding, it's really possible to finely tune the photon energy with steps of really 30 millielectron volts, but even smaller. And also the seeding also strongly increased the energy stability, strongly improves it. These are data taken in one of our first beam time, where the energy residual instability was on the order of 580%. Now Fermi can reach even smaller residual instabilities. Here you can see a picture of the synchrotron here, and the free electron laser is here along this line. So this was actually these characteristics were our original motivation for performing experiments at Fermi, because we were interested in observing nonlinear effects. So that's why we performed our very first beam time almost 10 years ago on LDM, where we tried to look to the competition in photoionization between the no resonance 2-photoionization and the resonant 2-photoionization. So the idea was essentially to slightly tune the photon energy and to observe the photoelectron emitted in the continuum. We wanted to have a look to the impact of a resonance on this photoionization process. So we performed the experiments. We were quite happy during the beam time to see an effect that we initially attributed to the absorption of 2 photons. But actually we realized afterwards that this was, our interpretation was not so, let's say, clear, because we could have also a competition between a path that at that time we didn't realize, namely the single photoionization by the second harmonic of the FEL, which is always present, even though it's a very weak, it's a spurious effect. If one is investigating nonlinear effects, this can play a role. That's why a few years later, we designed a different experiment based on the combination of 2 colors, and we could demonstrate the first coherent control in the extreme ultraviolet range. So this was a kind of the experiment. The very first one was not successful, but I mean, it led us to think about the possibility to create several coherent harmonics using a free electron laser. And this is already, when I discuss about coherent harmonics, we are already moving towards the attosecond field, because actually this is what we require in order to create an attosecond pulse train. We want to have, I mean, coherent harmonics of a fundamental radiation. So, and now we can switch to the time domain. So, because as I was already anticipating, if you have now 2 colors which are coherent to each other in the time domain, we will have a beating. So in this case, just the harmonic 7 and the harmonic 8 of Fermi. If you have 3 harmonics, we already have an attosecond pulse train. This actually looks quite different, slightly different from what we are used to using tabletop sources, because in particular also the spacing between 2 consecutive attosecond pulses is not the 1.3 femtoseconds that we are used to when we consider 800 nanometer driving laser wavelength for the iodine harmonic generation process. Here we have just 800 attoseconds, but the pulse structure is exactly the one of an attosecond pulse train. If we add up an additional harmonic, what is possible at Fermi, of course, we can define even better the attosecond pulse train and so on. So I was just to show you this very simple picture, because already when we realized that the seeded free electron laser could create 2 coherent harmonics, it was rather clear that we could generate an attosecond pulse train by adding additional harmonics. What was not so clear was how we could measure this attosecond pulse train. And of course, what the first things we thought about was simply to extend to a free electron laser what we know already very well in the attosecond community based on iodine harmonic generation. So the community, I mean, from which at least I'm coming from. So in this community, we already since 20 years, it's possible to characterize attosecond pulse train using the so-called Rabi technique that was first demonstrated in 2001. So in this technique, just to briefly remind you about this technique, technique is based on a 2-color photoionization. One color is given by the attosecond pulse train, where we have only odd harmonics of the fundamental radiation. The second color, it's an infrared pulse. So if we look to the photoelectron spectrum, which is created by the combination of these 2 colors, we will see that we have 2 main features. The first one, it's represented by the photoelectron peaks, which are created by the absorption of a single XUV photon. These are these intense lines in this simulation. And then we have additional lines, which are created by the absorption of an XUV photon, and then by the emission or by the absorption of an additional IR photon. In this way, we can create additional lines, which are so-called sidebands. And the important point is that because here we have the coherent superposition of 2 different pathways when we create a sidebands, so it's an interference process, we have that the intensity of the sidebands depends on the relative timing between the attosecond pulse train and the IR, and the position of the sidebands depends also on the relative phase between the harmonics. So, and this is actually what is used in the attosecond community. in order to characterize the relative phase between consecutive harmonics. Once we have this information, then it's possible to fully characterize in spectral domain the radiation, because we can combine the intensity and the phase, and therefore we can reconstruct the attosecond pulse stream. Now, if we want to extend this idea to the FEL, we have to keep in mind an important point. The point is that in order to observe this oscillation here, because only this oscillation can give access to the relative phase, we must have an excellent control of the relative timing between the XUV radiation and the IR. Not very good control means we must be able to control the relative delay on the order of few tenths, or let's say 100 attoseconds. If this is not the case, and we imagine to perform an experiment, this is what we will observe. So essentially a kind of noise. So we will acquire data for different laser shots, but we will not be able to observe any oscillation because of the large timing jitter between the XUV radiation and the IR. So typically, just to give you an idea, for free electron lasers, the timing jitter between the XUV radiation or X-ray radiation and the user laser, our infrared laser, it's on the order of few tenths of femtoseconds. Fermi has already reached a very, I would say, excellent characteristics in these respects, because the relative jitter, it's only on the order of plus minus 3 femtoseconds. Nevertheless, this is not enough in order to observe the oscillation. These are again simulation, what I'm showing here, which have been prepared using the typical timing jitter available at Fermi. So you can clearly see the oscillation are completely lost. Even though, if you look to the first two pictures, here you can clearly see that there is an important difference between the sidebands oscillation. Here the oscillation are perfectly overlapped in time. The two maxima are occurring at the same time. Here they are exactly out of phase. But when we lose the attosecond synchronization, this information is lost. However, and this was actually the idea that we applied and we developed, if we look to the correlation between the sidebands, we can still gain again access to this information. Because in this case, in the upper panel, what we would expect to see, and what we see, of course, in the simulation, is that we have a positive correlation, because the two sidebands, they are perfectly in phase, and therefore we have a positive correlation here. But on the other hand, for the lower panels here, the sidebands are out of phase. So the correlation between these two is negative. So our idea was actually, we cannot gain information about the synchronization. We cannot improve it up to the point where we can see sideband oscillation. So in other words, we need to find a different way to extract the information, and this is based on the correlated analysis of the sidebands. So the idea was actually to renounce to the control over the delay and replace it with the correlation analysis. This is, of course, not a new idea also for free electron laser science. Just to remind you, there have been already, excellent, very interesting experiments using free electron laser where this kind of analysis has been used. I just want to remind you the analysis performed by Frasinski here based on partial covariant mapping for the investigation of the dynamics in the formation of hollow atoms. But this was our, let's say, idea. And now, I will show you how we apply this idea to the case of Fermi. So there is another important difference at Fermi, and this is the energy spacing between two consecutive harmonics. I was discussing at the beginning the difference between two harmonics for the high-order sources, high-order harmonic generation sources based on tabletop. It's 2 IR photons. In the case of Fermi, this is actually 3 IR photons. So the distance in energy is 4.6 eV. So if we just consider additional single IR photon transitions, we will not reach the condition where we have the interference between different pathways populating the same sidebands. We will have a situation like the one shown in these slides. If you don't have this interference, we cannot use the Rabi technique. The way to circumvent this problem, at least in this case was rather simple, is to crank up the intensity of the IR and to consider also two IR photon transitions. Because now in this case, we can have two different pathways contributed by two different harmonics, which are leading to the population of the same sidebands. For example, if we look to the sidebands here, we can absorb one photon of the harmonic 9 and one IR photons, or in alternative, we can absorb one photon of the harmonic 10 and emit two IR photons. We will end up to the same sidebands, and also here we will see oscillations. Now, I will not go into too much into the details, but it's very straightforward to see that also from these sidebands, in particular by the tilt of the sidebands, it's possible to get information regarding the relative phase between consecutive harmonics. Again, the information that we need. In our experiments, what we did was to correlate the single shot of one sideband, for example, the sideband A, with the intensity of another sideband, for example, the sideband C. The interesting point is that this correlation is very sensitive to the relative phase between the free harmonics. For example, if the free harmonics are perfectly in phase, so all the free phases are equal to 0, then we expect to see a perfect positive correlation here. On the other side, if we start changing the phase of one of the harmonic, this correlation plot will change remarkably. In particular, if I hope you can see here, if the phase of one of the harmonics is pi over 2, we expect to see a very nice circular correlation plot. And if one of the harmonics has a pi phase, we expect to see a perfectly negative correlation. Now, already the shape of the correlation plot is very important because this gives immediately access to the group delay dispersion of the harmonics. The theory is actually very simple. It's simply based on the strong field approximation. One can consider the strong field approximation in the case of monochromatic fields, very long train out of attosecond pulses. And what one will see is that these two consecutive sidebands are actually composed by an average term plus an oscillating term. And these two oscillating terms, they are perfectly out of phase. One can then plot the two sidebands one against each other, construct these what we call the oscillating parameters, and one can see that the correlated plot of the oscillating parameters of the sidebands, of only the oscillating parts of the sidebands for free consecutive harmonics, it's always represented by an ellipse. So the correlation plot that we expect to observe, it's always an ellipse. And the eccentricity of the ellipse depends on this angle, delta phi, where this angle is nothing else than the group delay dispersion. So it's the difference of the phase difference between the group of free harmonics. And this is the information that one needs in order to fully reconstruct the attosecond pulse stream. So in other words, directly from the correlation plot, we have directly access to this parameter, to the group delay dispersion. We analyze then the data in a slightly different way to be more precise, but already the correlation plot, it's the informative about this phase, and this is exactly what we need. Another way to analyze the data or the simulation, and this is also the way that we are usually doing, is to use the so-called correlation parameter. So we define the correlation parameter of our correlation plots, and the interpretation of this correlation parameter is, of course, straightforward. If the oscillations are perfectly in phase, we expect to have a correlation equal to 1. If the correlation plot is represented by line tilted at -45 degrees, the correlation will be -1. And if you have a circle, we expect to have a correlation equal to 0. Again, according to the simulation, this is working perfectly fine in order to characterize the group delay dispersion. And here you can see the evolution of the correlation parameter as a function of the group delay dispersion of the free harmonics. So it's expected we have that when the free harmonics are perfectly in phase, group delay dispersion is equal to 0. We have the maximum correlation parameter is equal to 1. When the free harmonics present a group delay dispersion which corresponds to a phase difference of pi, this will be this point, we have that the correlation parameter is -1. Another important point is that this curve is not very sensitive to the IR. So you can see here for different IR intensity in atomic units that the evolution is much more or less similar. Only for the highest intensity here we have a kind of deviation. And this is, of course, very important because this also gives us the possibility to relax the condition on the precise control of the IR or on the precise knowledge of the IR in order to extract information on the group delay dispersion between the harmonics. The most important things, the most important correction to this curve, it's really due to the fact that we are considering only the strong field approximation. If we consider the solution of the time-dependent Schrödinger equation, so where also, photoionization phases and continuum phases are taken into account in the proper way, we see that there is actually, the shape of the curve is unchanged, but there is a small shifts on the order of 10 degrees, 9-10 degrees between the curves here, between the SFA prediction in red and the TDSA curve in blue. And actually one can, once this is characterized, one can take this small correction into account. So this was a long introduction about the idea that we want to implement. And now I can go to the experimental implementation. So we have performed two different experiments, one with free harmonics, the second one with four harmonics, and of course I will start with the most simple one, with the free harmonic case. So here you can see just a schematical view of the 6 ondulators available at Fermi. In the free harmonic case, we generate each harmonics using a pair of ondulators. So the first two ondulators are creating the harmonic 9. The central two ondulators are creating the harmonic 8. The last ondulators, they are creating the harmonic 7. This is the succession of ondulators and harmonics is done in this way because the lowest harmonic, they have the largest divergence. So it's better that they are created at the end of the ondulator chain. An important point is that in all free electron lasers, in order to rephase the phase of the electron bunch with respect to the radiation, between couples of ondulators, there are always phase shifters. Phase shifters are nothing else than small magnetic structures that are used in order to slightly delay the electron bunch with respect to the radiation which is created in the ondulators before. And we use this phase shifter in order to change the relative phase between the different colors, as I will show you now. The remaining part of the setup then looks very similar to a setup for the characterization of attosecond pulse train using high-order harmonic generation. So we have an IR pulse here, which is recombined using a Hole mirror with XUV radiation in a collinear way. And then the two pulses are focused together in a magnetic bottle electron spectrometer here. I remark here once again, tau is the delay between this attosecond pulse train and the IR, and this is fluctuating with plus minus 3 femtosecond jitter. So the first measurements that we have acquired in order to demonstrate this technique were acquired at low IR intensity. So you can clearly see here, also in the time of flight spectra, we can clearly see the main photoelectron peaks, but already we can see sidebands in between. Here two, here other two, and also here sidebands. Now, if we look to the correlation plot of the oscillating components between these two sidebands here, P7, 8, and the oscillating components between these other two sidebands, P8, 9, you will not see at this intensity, we didn't see something particularly interesting. One is, you can see a kind of circular correlation plot centered around 0 as expected, but without a particular structure. It's important to mention this point because the fact that we have still an extension of this correlation plot is due to the residual fluctuation of the single shot harmonics, which are playing an important role in the experiments. When we start increasing the intensity of the IR, you can see, of course, that the sidebands here are increasing as expected. We are transferring photoelectron from the main photoelectron peaks to the sidebands. But at some point, now we'll just go to the final, to the intensity where we run the experiments at 1.5 10 to the 12, you can clearly see that the correlation plot is assuming a really non-trivial evolution. In particular, it's assuming, a circular correlation plot. It's a kind of donut. And this is already the indication that we are observing a non-trivial, as I said, correlation between the different parameters. And this is actually already close to the effects that we want to observe. However, this is not yet enough. The other remarkable and the other important point, in order to be sure that the effects that we were observing is actually the effects due to the different synchronization of the harmonics, is to change the relative phase between the harmonics. And this is something that we can do, as I was mentioning, by delaying one of the harmonics or two of harmonics with respect to the others. For the next data that I will show you, we were using the phase shifter here, PS2, the second phase shifter installed in the ondulator chain. So you can imagine that this phase shifter is delaying the electron bunch with respect to the harmonic 9, which is created in the first two ondulators. So effectively, when we operate on the phase shifter 2, we are anticipating the harmonic 9 with respect to the harmonic 8 and the harmonic 7, which are created afterwards. We delay the electron bunch here. So we can look in terms of radiation, we anticipate the harmonic 9 with respect to the other two harmonics which are generated afterwards. And here you can see schematically, we can finally introduce phases with a resolution of few attoseconds here. So we repeat the experiments now at the intensity of 1.5 10 to the 12 watts per centimeter squared, the intensity of the IR I was showing you before, for different values of the phase shifter. And this is, what we could observe. We start with a condition where we have a linear correlation plot here. So if we calculate the correlation coefficients on these correlation plots, we get a value which is very close to 1. We change the phase, and then you can clearly see that here, when we introduce a delay of about, I would say, 35 attoseconds, the correlation plot already looks very different. It's more an ellipse, and this means also that the correlation coefficient is reduced. We keep going up to the point where we reach the maximum here. About a delay of 70 attoseconds, we have completely switched the correlation plot. We went from a positive to a negative, and here we are almost very close to -1. We are on the order of -8. And by keeping increasing the delay of the phase shifter 2, we can go back to the original position where we have a positive correlation here. So this is a clear demonstration that by changing the phase, changing the position of the phase shifter, we have really a perfect control over the synchronization between the three different harmonics. So we can really tune the phase of one harmonic with respect to the other with the precision of few attoseconds. We can quantify this with the correlation coefficients, and also the oscillation is perfectly following a sinus or a cosinus oscillation. So this curve at the same time demonstrates that we have this control, but also this curve is very important for our application because it works as a kind of calibration curve in the sense that we can assign with this curve to each position of the phase shifter the corresponding group delay dispersion, the phase difference between the group of the three harmonics 7, 8, and 9. And this is the information, as also we show in the manuscript, it's very simple to see. This is the information that one needs in order to reconstruct in time the attosecond pulse train. But now you can also appreciate, I mean, the novelty of what can be done at free electron laser, because having the control on the group delay dispersion, we can also shape the characteristics of the attosecond pulse train in phase, and as I will show you also in amplitude. So as a first application of this technique, we have acquired data and reconstructed the attosecond pulse train for different phase configuration. So here you can see the free harmonics, here still in time of flight. So these are the free harmonics. You can clearly see that, and here you can see the correlation plot for 3 different phase settings of the harmonic 9. Here probably you can only barely distinguish that there are 3 curves superimposed. That's actually a positive point, because it really shows that independently from the phase of the free harmonics, the spectral intensity remains almost unaffected. So we can change in a selective way the phase of one harmonics without affecting the amplitude of the harmonics. And so we can really go from a situation where we have a positive correlation. It means here the group delay dispersion is 0, the free harmonics are in phase. In time, we have a nice attosecond pulse train. We can go to a situation where the phase, the group delay dispersion, the phase, the corresponding phase is pi over 2. We have still an attosecond pulse train, but we start developing a satellite here. And then when the phase difference is equal to pi, we have a negative correlation, and we have a very, let's call it dirty attosecond pulse train. So we have more or less, I mean, a noisy structure. Still, I mean, we can control it, but we don't have well-defined attosecond pulses anymore. The important point is that the amplitude is not affected here. However, free electron laser, they offer this big advantage that is possible also to control the amplitude of each harmonics. For example, playing with the undulator gaps, playing with the characteristics of the electron bunch without affecting the phase. So that's why in another experiment, we were changing simply the amplitude of the harmonics, playing with the undulator gaps. You can see here 3 different conditions, the blue, the black, and the red one, where we can change in the phase of 1 or 2 harmonics. And you can see from the correlation plots that we are not remarkably affecting the synchronization between the free harmonics when we perform this operation. In other words, if you look in time, you can always see a nice attosecond pulse train here. Of course, only the height of the peak is changing, because also the energy content here is changing. So these data really show that it's possible to perform a complete attosecond pulse shaping in amplitude and in phase, which can be also extended to the case of 4 harmonics. So we acquired additional data. We have now, I mean, several data also with 4 harmonics, and in which, for this case, I mean, each harmonics was generated by an independent ondulators. In the measurements I will show you, the last 2 ondulators were not used. And here we can really play with the phases of each harmonics independently using the phase shifters. So we can go from a condition where, for example, we have that all harmonics are in phase. It means the correlation plots here that we consider are perfectly linearly, they show a perfect correlation, and we have a nice, well-defined attosecond pulse train. Of course, now the additional complexity is that because we have 4 harmonics, and we need always to characterize the group delay dispersion of group of 3 harmonics, we will need to consider at least 2 correlation plots. That's why you can see here now we have the correlation plot of P7,8, P8,9, and then the next one, P8,9 versus P9,10. So, but that's, we always need to consider group of 3 harmonics in order to get the relevant information. But we can play independently with this group delay dispersion. For example, we can decide to leave one unaffected, like in this case, and start playing with the synchronization of these 3 harmonics here to get, again, a nice circular correlation plot. In time, this means that we have, again, a nicely attosecond pulse train, but as we saw in the case of the 3 harmonics, we start developing a satellite here. We can also have funny structure. For example, in this case, we can put the 4 harmonics to be characterized by a negative correlation, both groups of free harmonics, and this corresponds in time to a double pulse structure here, and so on. So we can also have an ellipse in one case and the circle in another one. So we can have really full control on the intensity profile of the attosecond pulse train, and you can see that Fermi can be considered as an attosecond pulse synthesizer, because being equipped with 6 ondulators, it's possible to create 6 harmonics and really play independently with the phase of these harmonics. To the conclusion of my talk, so I show you that it's possible to characterize the harmonic phase difference in the harmonics created by a free electron laser using an extension of the Rabi technique based on the interference of 2 IR photon with 1 IR photon pathways. The correlated analysis that I show you allows to get information on the group delay dispersion of the harmonics, and this is the information that one needs in order to characterize in time the attosecond pulse train. Another very important point, which I was not addressing in this presentation, but of course is there, is that the energy that we can achieve at free electron laser, it's typically larger than the one that we can get with high order harmonic sources, on the order of 10 microjoule. Of course, there are also sources now, harmonic sources, who can reach this energy range, even though there are not so many. For sure, the unique characteristics, however, is the possibility to control independently and selectively the phase and the amplitude of each harmonics, and this is really a unique characteristics in order to perform an attosecond pulse shaping. And I think, with this, I would like to thank you for your attention. And I will probably stop also sharing the screen.
So thank you so much, Giuseppe, for a really nice talk. So there is a question from Andres Ordones. Thanks for the great talk. Can you play with polarization of the harmonics, control them independently of each other?
We have, hello Andres, by the way, we have not yet tried, we would like to. I don't know if we can play independently with each harmonic, but we would like for sure try to create, let's say, attosecond pulse with a, not linear polarization. This will be the first step. Then if we are successful in this step, we might consider in an additional beam time to mix polarization for each harmonics.
Okay. So, hi, Giuseppe. Thank you for the talk. So basically, I guess you would need to rotate the ondulators, right? So this is possible in Fermi. Okay.
This is possible. You can create circularly polarized XUV light. This has been done at Fermi in several experiments, left and right, also, combined. What I don't know, because we have never tried, it's whether you can, for example, alternate for each harmonics, left and right, and still characterize the attosecond pulse trains.
And then to just continue with this kind of polarization stuff, I know that in optics, so when you focus your beam a lot, then you get a longitudinal component, and then you also get kind of elliptical polarization. So to what extent can you focus your harmonics in Fermi? What would be the typical, because of course there is a limit to this, right? The wavelength. Mm-hmm. But so how far are you from that? Because you actually have to go more or less to that amount of focusing to see this longitudinal component emerge.
We are not so close. We are still, because the typical focal spot size for the harmonics are on the order of, let's say, between 5 and 10 micron. The wavelength here, it's on the order of few hundreds of nanometers. So we are still quite far from the diffraction limit.
And what are the physical limitations to go to this amount of focusing?
I think the main physical limitation, I would say, probably is the distance between the focusing optics and the interaction point. which is on the order of, I mean, I might be wrong now, but 1 meter, 2 meters. So you will need a tight focusing, I mean, for going, I mean, large numerical aperture, I mean, to go very close to the diffraction limit. And the end station where we are performing the experiments, it's not designed for doing this.
Okay. Thank you.
Thank you. So we have a question from Diego Arbó. Beautiful talk. Question: what's the target for the photoelectron spectra in your last slide before the conclusions?
So for all I mean, now I have to look. Because for the free and four harmonic was neon. In the last measurements, this I will need to check, but I think it's again neon. Actually, we always use helium and neon, but the most of the data we have in neon.
Okay, thank you, Giuseppe.
Diego.
Is it published somewhere, these results?
You mean the very last one, or?
Yeah.
No, the very last one, no.
Okay, I look forward your publication soon.
Hopefully soon. You're welcome.
So we have another question from Hezvan Tahuri. Thanks for the presentation. Can you produce isolated Attosecond pulses in some novel way?
That's a good point. At Fermi, I don't know if we can. Yeah, there are, I mean, we also discuss, I mean, I think people at Fermi, they have some ideas. They are very preliminary. But in the current condition, I would say no. Isolated, no.
Is that okay with you? Would you like to ask further? Seems to be fine. So Carlo Calegari would like to speak, right?
Okay.
Go ahead.
Yeah, this is just, well, first of all, thank you, Giuseppe, and congratulations for a great talk. This is just to confirm that at Fermi, it is possible to control independently the polarization of the different ondulators. But as Giuseppe was rightfully pointing out, the issue is also that of detecting the effect. So the geometry of the experiment is rather important, and this is why the experiments that had been presented were done in vertical polarization, which is, by the way, the most difficult to achieve at Fermi. So, and concerning the dimension of the focus, we work at a fixed geometry because we cannot move the end station around. And so the focus size is essentially determined by the ratio of the entrance and exit arm, and by the diffraction limit at the source point. And this results in the tens of microns that Giuseppe was reporting.
Okay. Is there anyone else who would like to make a remark, ask a question? Do feel free to do so. I don't see any. So for those who are joining from everywhere, and also for those who are watching on YouTube, thank you so much for supporting us. And let's thank also the speaker for joining. And see you soon.